video we will gonna go starting our diffusion model journey till now till now what we have covered I want to just give you the idea of that so till now what I've covered we started from autoencoders and we moved to VAE and then GANs, and these are the generative models. And these are the generative models. Now we are going to the next generative models, which is the one of the best generative models right now. This is a diffusion model. So, and this model has been just outperformed the existing benchmark records and in various metrics of generation. So, and this model has shown the promising, isn't it? Promising. So, and so let's move into our section. So what is our section? Section 10. So this is our section 10. So 11 we should go 11 manipulate the diffusion model. So let's start our so this is the plan of action of today's. So we will gonna go take out the overall look of the diffusion model. So and this video will give you the idea of how diffusion model landscape is there so you can just from this video you will get that whole idea of it. So before going into that definition part I want to show you the things that I have liked the capabilities that I have been impressed by this. So this is the video which has been created by this latent Sora model. So it is a diffusion transformer model. So let's see what it has created, isn't it? And I have been just astonished by this. So you can also this is like a motivation for using. So let's look at it, isn't it? This is created by the AI. That's such a realistic, isn't it? Isn't it? So and another video that I find is so interesting is also a video. This is so beautiful. This is also this cat this is such a realistic outcome. So you can just read it the and check. I think it's showing such a realistic expression here also. And so I think diffusion model really from this text prompt it is creating such a art this is such a creativity isn't it? So this is created by DALI 2 isn't it? So it is also diffusion model. So DALI 1 is not a diffusion but DALI 2 from the diffusion model started appearing. So after that another video is this we have already watched and the reflection. I think this is also so this is the this is where is the prompt. I think there's prompt. I think this is the prompt. So reflection in the window of the train traveling through the Tokyo suburbs. And this is the prompt given to the diffusion model. So this is a video diffusion. So video model, not images. So but based on diffusion models, just I think it's capturing some of the physics, and so you can just reflections. You can just see the reflections and the shadows and something isn't says capturing. So nice, isn't it? This is and there are several art but I isn't gonna go into that. So you see the art and let's take at it is in the definition part isn't it? What are diffusion models isn't it actually isn't it? So these are the class of generative models. So generative models we have already this is a class of generative models that create data and they are generative models so they will create data and by gradually transforming a simple distribution like Gaussians. We start from Gaussians and into a complex distribution. So we can't approximate this P of X, which is the real data distributions. And this is our the distribution of data images. So images. So from will create data, as in create the data from this distribution p of x by gradually transforming a simpler distribution like a Gaussian, as in a Gaussian distribution. From this is the standard Gaussian distribution. From this we will map this into this distribution, as in through our generative models. So this is the generative power of generative models. The estimating this is involves any intractability and such a computationally is impossible task is right now. So and like this will just transform create data as by gradually transforming a simple distribution such as Gaussian noise into a complex distribution like images and other data types. They are based on the idea of diffusion processes. So diffusion processes. Let's move on to the diffusion processes. What is diffusion processes? So diffusion is, so as we have as already written, if you are read or not doesn't read, it doesn't matter. So diffusion process is just as in like I will just give you the physical intuition also through the video. So diffusion processes is something that's the in a solute is in a solute, it's a solution. So solution, and this is solute is in solute. When this is solute, this is has some structure. This is the p of x. This is p of x. It has some structure, some attributes, and some things. And when you dissolve it into this, it will lose structures. It will lose structure and completely being be soluble. And so yep, the and which it become uniform or normal. It will become just soluble, and it will just become normal, and the all solution will look like same, isn't it? So and we want to, isn't it? From this we want to go back to this original, isn't it? So we want to from this simple, we know this is the this thing we know, isn't it? This is uniform, this is Gaussian. So in case of our image, this is a Gaussian. We start from Gaussian, this is Gaussian, and we go back to the data distribution p of x through undoing this process. So undoing this process, the mixing process, we undo that, isn't it? And we we from this distribution we learn to go back here, isn't it? Here. So and in physics it seemed like a extremely difficult task, isn't it? But there have been some mathematical, isn't it, mathematical derivations and reverse times diffusion. So in so there have been some mathematical work which we're gonna go look at, isn't it? So we can go through the mathematical way, and if we isn't it, in a much more, isn't it, simpler way, isn't it, the if we go into more details in detail of the diffusion process, we can find this reverse time, isn't it, of it, isn't it? So and over here, isn't it, the base idea of diffusion process where noise is iteratively added to the data in the forward diffusion. So we destroy the data. So we first of all add the noise, we add noise iteratively added to the data in the forward process, and then gradually remove in the reverse process to generate data. So this is just a definition. We're gonna go look at it in a more detailed and more refined listening. So if it doesn't get it, isn't, it's okay. So because we have just this definition will give you the broad ideas and what are diffusion models, and just we're gonna go just the definition will start making sense when you move forward. So after that, let's move into some of the different parts. So history of diffusion models. So the history of diffusion models lie theoretical background in mathematics and physics. So there has been some key papers, like which I want to show. So something why not gone. So if I can, so yeah. So this is the paper, I think. I will show you the Anderson diffusion paper. So this is some of the paper, I think, reverse time. So this is some of the mathematical foundation has already laid out, isn't it? For this is concept of diffusion has been actually taken from the physics and mathematics. So these are these papers, foundation papers, which has reverse time diffusion equations. So and there are several paper like this, isn't it, which led the foundation of diffusion models. So let's look at the definition also. So what I've written here. So the concept of diffusion in probabilistic models can be traced back to early work in Markov process. So what is Markov process? We'll also look at it. So early work on Markov process and the stochastic differential equation. So these are these isn't it, the the key work isn't it, stochastic differential equations, and they laid the ground. These ideas laid the groundwork for the later development in the generative model that utilizes diffusion processes. So let's understand the diffusion process in physics. So the concept of diffusion actually originated from the statistical physics, isn't it, which describes, isn't it, how the particles, isn't it, split over time, isn't it, like in our case, isn't it, our image, isn't it, how the noise, isn't it, get distributed, isn't it, into our, isn't it, image. So in the same way, isn't it, the particle distribution, isn't it, through the under the influence of random addition, through the addition of noise, isn't it? So randomness, isn't it? So this idea is actually found in the, isn't it, physics, isn't it, statistical physics, and they model this is using SDEs in stochastic differential equation. So and these are these, some of the foundation work, isn't it, which led the diffusion to go forward, isn't it? And let's understand what is the Markov process and what is stochastic differential equation and how they are playing the role here, isn't it? So Markov process, isn't it, is like this is if you have a sequence of events, isn't it? So we are just understanding the basic things. So if you does not understand those, isn't it, we I have not show the forward process, reverse process, but just understand this concept. So this is just a Markov process, a series of actions. And this is the events, this is xt events. And this is xt minus 1. This is just events, guys. X0, this is just events. So from here we to move to t, so there is more action also, and there are more actions here, and so that, and this action xt only depend on this xt minus 1. So this is the Markov process. So when this is the Markov process, and what is stochastic differential equation? The event, the probabilities, not the previous one. It does not depend on these ones. Just it depends on the probability of xt only depend on the preceding events and just back events. This is the Markov process, and how the stochastic differential equation actually playing a role, isn't it? So SDs and play the role in modeling and diffusion processes. So it actually describes, isn't it, how a particular systems, isn't it, evolves, isn't it, both, isn't it, deterministically or stochastically, isn't it? So random components, and you can just say, and it is, isn't it, this concept has been used in the, isn't it, uh, in physics, isn't it, such as, isn't it, random particle random particle of the motion of the particles. So and other topics, and also, isn't it, in financial markets it has been used. So this is the some of the foundation work in diffusion models. And let's look at it, as in we'll also, isn't it, go into the idea origination part, how the physics, isn't it, actually, isn't it, play a role here, isn't it? So let's see the some of the impact right now, the diffusion model has happening, isn't it? The impact, the first impact, isn't it, that everyone can see is in the, isn't it, field of art and creativity. So artists, isn't it, can actually, isn't it, come up with the new art, isn't it, very quickly, very quickly, and just test their hypotheses, and just with the little knowledge of artistic trainings, little knowledge of artistic, then they can just go and just learn, and just not learn, but just experiment their hypothesis and just improve the guidance. It will give some additional, to creative people. It will just add, more, more paces, and make them more efficient, and also they are replacing in some cases. So and you can see the some of the art, that I've already showed you, and I will not gonna show the art, because you can show, in internet. So art and creativity, and after that it has been used in medical imaging and molecular discoveries. So the diffusion processes is such as reliable, it has so fundamental, background, and it's a really, has a wide range of applicability areas. And so from from physics to it can just it is just going to the every each and every field. And so and another field is molecular imaging, such as imagery. You have the images of x-rays in x-ray CT scan, and it can be used in noise reductions and reconstructions if some part is it's not good, isn't it? And in molecular discoveries, isn't it? Molecular discoveries like many models like in protein ligand binding, isn't like diffusion or docking, isn't it? Protein ligand docking and other domains, and this has been so much extensively used, isn't it? I think diff doc. I think this is the diff doc. Some of these I heard, isn't it? The diff doc and torsional diffusion, and there are so many, isn't it, ideas in molecular diffusions and torsional diffusions and other idea what I can see members in it. Torsional diffusion diff doc and alpha fold also, isn't it? Alpha fold 3, isn't it? Alpha fold 3 and others in protein molecular space, and in molecular spaces, there are so many things and so many. And in the simulation, like in how the climate in climate change also, in climate and environmental simulation. So if you want to see this how the system evolves over time, using the diffusion models, you can just use this and run this in effective simulations through the diffusion models, and just experiment yours and plans and what you have made and policies what you gonna made, and just run the simulations and see the effect, isn't it? How it's gonna happen in the how it's gonna go evolve, isn't it, over the time, and see the research. And it is another application is scientific resources, isn't it? Simulating folding of proteins. So like how the protein fold, isn't it, in 3D structure, isn't it? Which is which helps to actually know the function of the protein, isn't it, through the structure. So and just running some of the complex quantum level particle simulations through the diffusion models. So diffusion models has a very strong background, very strong in mathematical foundation, so that it can, and it is such a stably, we can control the generations, and it is really, stable while doing like complex simulations and doing some high level computational tasks. Content generation, as you can see, we are seeing the like the good quality of content, like for the YouTube thumbnail also, and which people are creating some of the thumbnail, and not only YouTube but also the some of the from the script, they can just create the videos, and this is such as introduction videos and other videos they can be created, through the sensitive content generation. And in others financial economic markets, it has been highly used, so it can help in financial market also, so and less what are the ethical concerns we are, some of the ethics and concerns we care about, so I think the fake and content authenticity is something we have to work on. So these are the part, and the biasness and the fearlessness. So this are some of, because how we train the diffusion models it can just contain the data which are primarily driven for primarily collected in a bias driven way, it inherently contains some biases in it, and it can really do some bad harmness to the society and people. And let's move into the what this brings. We have all these models, what we have read, we go from autoencoders to VAE to GANs. Right now we're talking about diffusion models, and there are also flow matching and energy based models. But why? What it brings, to the table, So that's the question, So there are here are some of these, some of the benefit it provides, so it provides training stabilities in compared to others, the training stability is so much stable than GANs, and other architectures other architectures are also stable, but the training is so much stable. And genetic process is controllable controllable and it is you can just do iterative 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 so and iterative approach, so you can just just take the input which has in process at the middle so we will understand so with the diagram we move on, so we will understand this part and the mode coverage it actually covers all this mode of data modes of data distribution. So data distribution. So if your data look like this, it will cover all these modes of the data. And so this mode, it will cover all these modes of the data and all these nuances of the data. So it will capture the whole distribution. It will learn the whole distributions and it will not leave out the any of these spaces. So and sample quality the sample quality is so much good and it has the FIDs which is very good very good FID and another scores other aesthetic score and other metrics which is used to measure the quality of the images and the flexibilities it can easily combine with the architecture with VAEs VAE and GANs and other architectures. So it has so it can easily adapt with other architecture and the speed speed has been some of the does not at the initial times it does not it produce slow generation and speed is slow, but right now there have been significant improvements in speed so because of these new techniques they have just come up with so significant improvement there have been. So there have been significant improvement right now and a strong theoretical background from physics using Lagrangian sampling and the other techniques like there has been a significant progress right now. And what's the capabilities it has so we will gonna understand what are the capabilities it brings. So another is some of these guided diffusion, so you can guide through the image text and other modalities. So text is sketch and image and other modality you can just add like description. These are some of the modalities where which guide the diffusion processes and generate it as what you like basically. And this is just a conditioning see this is what this guidance diffusion is actually doing is it is just guiding guiding the diffusion process to your desire according to your prompt your image and your sketch and image, and you are just guiding the what to generate and how to generate how not how to do what to generate it's just giving this guidance so it is there has been a significant it has such a good capabilities while doing guided generations. And another thing is the mode coverage and it covers the actual all modes of the data and superior fidelity. The quality is astonishing. So higher level of quality has been achieved by this models, and it has the control over generation steps. So tool is we can just add so much control in each generation step. So noise reduction is how we can do is like how we can add noises and as we move forward we have just control over the generation so much so like how we gonna go if you want the some middle layers we can just change the tweak theirs differently to our according to requirements and just use the intermediate representations for our purpose isn't it? If we need that isn't it? And scalable to high dimensional data isn't it? From video to 3D data isn't it? It can really scalable isn't it? So this is some of the important properties isn't it? We are some it is really isn't it, good at video generation. What I've showed the videos in earlier. So this has been it's such a this is the diffusion power. So this has been the they are so much scalable in the video data also isn't it? So they have such a good as in dimension. So they perform such a due to their iterative refinements also and because they does not learn at one go and pass it and just predict the as we do in GANs. So it will just time steps and step by step it will just iteratively do so what iteratively you will understand it isn't so and other modalities isn't it like other modalities and processes isn't so like as in other diffusion processes. So like in the real world lesson you can just I want this example lesson you need to understand the diffusion process. So we will listen will look at it later and so what this process is isn't it? In like rather than images and we can move on to the other modalities but isn't it? First to understand other modality we need to understand the image modalities. So I will explain later it. So what is the idea origination? So the idea origination. So what's the physical intuition isn't it? So I have already discussed in part and I want to even give you the more physical intuition isn't it, of it. So how the idea is actually originated. So if I can see so this guy's video. So let me. So I will gonna go take the reference from this video and so given by the creator of the diffusion models. So first paper he is the guy who would first come up with this idea of diffusion was other guys also but he write the 2015 papers which actually laid the foundation for the diffusion models. So and in this video he say that the physical intuition and time reversible. So he claims he just gives some of the ideas that we we first of all destroy the structure in the data like we destroy it isn't so I will show that if I so there is a dye so dye molecule. So if I can just lower it so that you can understand it. So observation. So he started with the dyes dyes which actually represent the data density and when it is when the dyes go and it will become just so learn the structure of this density. So we have this dye so water and this dye we want to learn this dye which the data distribution of it can be of images and it can be other modality also. These ideas so and observations so diffusion destroys structures. So as when it diffuses the structure of this dye will destroy so from the our data when we add if you are starting with the images so I will use this some of the other tools also. So if I can so this is so if you start from the images and if you start adding noises like Gaussian noises so we're gonna go later on understand it more clearly but the if we the diffusion the diffusion process what happening here is actually destroy the structure of the data so if you start from the noise images and you start adding noises so it will actually destroy the structure. And he makes some certain observations like this observation on diffusion destroys structure of the data and the data distribution this dye distribution actually make the make uniform and the core idea is recovering structure by reversing the time so this is the question he asks and what if we could reverse time. So in physics this seems hard but isn't it using techniques recovery tradition by starting from uniform distribution and running backward dynamics so this is the idea recovering the structure by reversing the time so if we look at this so this idea is recovering data distribution by starting from the uniform distribution and running backward dynamics in real world is pretty hard so or even not possible and but if you go more into the inner dynamics of this dye in a molecular level you see this Brownian motion so and in Brownian motion the microscopic diffusion is time reversible so in that case the time is reversible so time reversible you can the diffusion process is happening so here just to show this how the this is the forward forward motion what you see here it's a forward motion and he's again play the backward motion and it has same exactly identical form so backwards and they have same as any functional form so the if the forward process is Gaussian in our image case and the backward process will also be the backward of diffusion will also be the have the same functional form the Gaussian functional form so this is the idea they can take it so they have identical forms so position updates are small Gaussians so we doesn't need it. This is the idea they take it from this observation so both forward and backward in time they just give the idea of that so this is the ideas which we have take from this observation what we have done right now so this is a physical intuition I have shown the physical intuition to you and let's move into another part what are the paper in diffusion right now so papers so to look at the papers that come into diffusion the first paper actually come in 2015 by this guy the video that I have shown written by this guy and other three people from Stanford so this is a team at Stanford created this as an first paper. I will show that paper also so if I can diffusion so this is the papers in 2015 paper so this is the paper this is the first paper came in the next video we're gonna look at this paper also so this paper actually introduced the idea of diffusion so and other paper is in this another paper from UC Berkeley I think so they created more applicable applicable and more result they show the results of the ideas they propose here and they also add more things like the connection between the probabilistic diffusion model and denoising score matching with Langevin dynamics so they also add extra things so they this paper from here the diffusion start progressing diffusion models and get traction more after that we're going to look at this both of the papers and there are also several other papers like in this 2021 improved DPM and the classifier guidance and some of the paper will just I'm just writing some of the core papers so core papers some starting papers so and there are some this paper is are the most fundamental papers in the diffusion landscape and these are the papers and so let's move into the application modality part so applications can be seen as to model as to models flexible high dimensional data modeling so they can use in high dimensional data modeling and act as a sampler as a sampler for generating new samples under active guidance and towards tax desired properties and so You can do guidance also, but also tasks that properties need. And it has been in involves problem like in painting, deblurring, and just infilling and other tasks like high resolutions, not high resolution, super resolutions, and other tasks like we have some images and you just remove some part and try the model to fill this part and try to fill this part. So I will show some of these images. So let's look at this so, application part. So there are some of these applications and come with this are the painting, restoration, translation, editing. These are these tasks in image super resolutions, editing. These are the tasks in the diffusion as really working good is in. So you can see this is the input and this is a DALI VQGAN. This is it. This performance has been super resolutions result by Latin diffusion models. So these are these super resolution work, and this is in painting, isn't it? In painting tasks. So just remove. Look at this guys. Look at this guy, and we remove this face of this guy and generate this from this guys, and we remove this and it's work better right now in this case. So and this guy, and we remove this face here. This guy become like this. So and video generation as we have already seen, isn't it? So what happen if a hole in the volume, if a hole in a volume hole appear in the volume? So this has been the figures in this type of task that can be used. And it can also use in generating data sets. So you train the models if you have less data set and you can just synthesize more data for your tasks. From generative model can effectively advance your task like classifications. Recent work have begun to utilize diffusion model to achieve this goal for vision tasks. For example, Telugu and collaborators adapt diffusion model to make efficient data augmentation for few-shot image classification. And these are these in image synthesis domain and point cloud completion and generation part and anomaly detections. Powerful mechanism for anomaly detections, modeling normal or healthy reference data, utilize the DDPM to crop the input image and reconstruct a healthy approximation of the image. So these approaches may perform better alter based on the adversarial better than the based on the adversarial training. So these are the some of the and also it has been applied in the domain of natural language generation. And from this multimodal generation we'll look at it. These are the applications in domain of this, isn't it? So and life sciences as I've already discovered from physics, biology, isn't it? Just in every domain, isn't it? Just as in applying from running simulations to solving some of the complex problem which can be solved by this densities modeling and the diffusion policy. So we will also look at it as in a robot policy. So this is reinforcement learning domain. So it can be used at that domain also and robot making the policies for the robots and material design is we have a different property and you diffuse this property and come up with the desired properties so it can be also in material generation. So we'll also look at it as when understanding become better so I'll give it this how we diffuse how the diffusion happen here in this part and in this part. So just overview I will give it this so and the vision and audio generation also there have been quite progress and this multimodality. So multimodality generations. I will also gonna take a this from here. So and from we have coming from the text to image. So from one data modalities like text to you can go to images. Just you can see the Latin diffusion. This is created by Latin diffusion models. So and this is the prompt. So same prompt, and this is given by imaging Latin diffusion models and theirs. And actually capturing such diverse data modality here. And so and a spoon. So they have been just other darks are scene graph to image generation. From graph we are actually generating images and text to 3D generation like videos that are in a wide range of application, including gaming like gaming 3D content generations. 3D content generation has been high demand for a wide range of applications, including gaming, internet, and robotic simulations. 3Ds and text to motion. So the multimodality. We are not from the text. We are doing several things. Text to video and text to audio generation. These are the applications part. Multimodals. So diffusion models. Just as it's not just to apply in text. It is from natural language to from language to vision to other modality also from text, image, video, and others. Graphs is from graphs. It can also work on graphs and others. Other data modality. It can actually work as efficient in all these modalities. Let's move into the another part. Is the advantages and disadvantages of diffusion models. So diffusion models are pretty scalable. You can just add more and more parameter into the network and scale for the higher resolution also. It has been performed very well, very well in compared to others. The scalability of the diffusion model is very high. You can stable diffusion 3, I think it has nearly 8 billion or something parameters as but some 8 billion parameter I think. So the parameters space can be grown so there is for high quality generation you can just scale up the models it can if you want to really obtain good quality images scalability is needed so it absolutely provides the scalability with stability and it can be combined with other architectures and techniques isn't it? You can just combine the two of the best world like diffusion and transformer GAN and transformer and you can arrange in such a way that the yield is maximum results so we're gonna go see the architectures which combines the architecture of both the architecture of VAE and all the other architecture we're gonna go see what it has. We can just combine different architectures. This is the advantages of GANs, isn't it? They can easily flexible to others in architecture also, and the interdisciplinary applicability. So they can be applied in many fields, like from temporal data modeling. So temporal data, we can just see here. In this slide, I will also show you at the end, but They are the multimodal application. They are just look at here, isn't it? Temporal data modeling. So from time series analysis to work from signal processing to all these fields, they have the advantages of applicability into every domain, isn't it? From audio signals to audio to and other field of sciences. So they have the interdisciplinary applicability and really have, isn't it, stronger impact to making them each field isn't better, isn't it? Each discipline better, isn't it? This is the power of diffusion models. So and controllable generations, you can just guide it, isn't it? Just guide your diffusion so well, isn't it? To generate to generate a desired properties, isn't it? For molecule, and you can just optimize, isn't it? You can just optimize your generation in such a way that you get desired property and desired attributism. So there is high controllability here is in presentism, and also easily you can control this isn't it? Rather than using other techniques like VAEs and other thing. So it provides better as in controllable generation than other thing. And let's talk about isn't it, some disadvantages it brings, isn't it? But isn't it, there are this is some of the advantages, some of the disadvantages you can see in fencing, because we have to in we does not just output in one go. So in GANs we just pass the noise and we directly get the clean images, isn't it? But here now, isn't it, we will not gonna get that, isn't it? In multiple time step, we have to run. We have to just remove noise iteratively, isn't it? The iterative nature, isn't it, makes this inferencing a little bit harder and take much more time while to generate new data. So it is it takes more time than other compared approaches, but there has been significant improvements techniques here, isn't so. And modeling discrete data. So in this diffusion model is actually inherently built for the continuous data. And if you want to model the diffusion model for the discrete data, then you have to do additional things additional methodology you have to apply for. You have to use the discrete diffusion models with different techniques, as any which we will discuss in later, isn't it? So there we have to apply different techniques, and if we go to discrete modeling, so we will discuss about this, and you can also look at this, and there are several techniques to that, and it require more data. So guys, to understand the data distribution, as in distribution, to capture the whole graph of distribution, it require high data, because we have to do reconstruction at every time step. So when we start understanding diffusion from scratch, so you will understand that, because but right now it when you are just you will not understand, but I haven't just explained the topic easily. So but right now for that it require more data, because you first of all add noise to the data and destroy the structure of the data, and you try from this noise you want to reconstruct it, isn't it? So you need efficient data, isn't it? Efficient data to capture the whole distributions, and you need compute budget, because these models are have billions of parameters, and the complexity that deals with is high, and so you need a good amount of GPUs. So let's move into the architecture part. So in the architecture for diffusions, the this is the noise. This is the first architecture, unit architecture. In the first paper, they introduced this architecture, and this architecture just take images and just output images. So, and this architecture efficiently do the job of prediction, noise prediction, and this is latent diffusion model. So LDM. So this LDM is actually the foundation for the stable diffusion. So they just scaled it up with any stable diffusion. For this is the latent diffusion architecture, which actually incorporate, this is a pure, this is this architecture here. So if I can draw it, so this green part, the green part what they are showing is actually diffusion, and there is, this is a VAE part. So this is a VAE part, encoder part. So they and this is the unit part. They have unit part, and they do diffusion not in a pixel space but in the lattice space. So if you have understanding of lattice space, so you will get it. So pixels are expensive. They say, oh, the pixels are so much expensive, we will not gonna go do pixel operation. So we will just, this pixel operation is expensive for us, so we will do diffusion process on this lattice space and create some of the astonishing results in the field. So this is the, and this is a combination of diffusion denoising, diffusion GANs. I think this is a denoising diffusion GAN. So this paper actually uh, tell us, how can we combine the diffusions with GANs. So this is the diffusion GANs, and this is the diffusion transformer. So DIT, and this will same do the same. Just pacify the images and just pass through it, and it's work like a vision transformer, but there are some external modification made here. And this is another diffusion. So this is a cascaded diffusion model. So which function is just to make this image more high resolution from this 32 by 32 image. This model is just this model just used for uh, making the resolution more higher resolution images. So, and this is efficient because you can just, if you have a budget of training, so you can just train this model separately and then do the super resolution. First of all, you create the generative models which create 32 by 32, and you can just do a super resolution, if you, super resolution SR. So and you again apply super resolution and you get this. So rather than just working into this whole spaces, whole 256 comma 256 spaces, you just reduce this. So you can just, this is efficient in operation also. So this, the cost of moving from here to here is lesser, isn't it? So you need not much parameters, isn't it, to do this operations. And this has been applied in the field, isn't it, so frequently, isn't it? You can see, isn't it, like, and this is the image gen by Google, which is, which use this cascaded model here, super resolution diffusion. So this is also text embeddings, and this is the text embedding. So this is a text and frozen text encoder, and this text embedding goes to text to image diffusion model, and then super resolution, and again super resolution, and it will finally give this images. So this is the image and video architecture. So if we have, and these are the some architectures. So this is used for video generations. And the video that I have shown you earlier is earlier actually work on the this diffusion transformer, but they have different architecture. The Sura I have shown you earlier is actually do diffusion. This is actually a diffusion transformer. So this is it, and let's look at the comprehensive summaries of this diffusion models from this comprehensive diagram. I get it into GitHub, so you can just search this diagram and you can find it if you need. And let's understand from this diagram. So in algorithmic space, it in efficient sampling, improved likelihood, and data with special structures, discrete data with invariant structure, data with modified manifolds, known manifolds, law manifolds. These are the some of these in algorithmic space. In optimization, noise schedule optimizations, reverse variance learning, and exact likelihood computations. So and in SD solver, for like learning free sampling, like SD solver and the OD solver, and the connection with other. See the connection with other generative models. So it has connection with these models. So it has a strong connection with these models also. So we see the latent diffusion model in using BAEs and normalizing flow and autoregressive. models. And other that then that is the application part. So let's look at it. So it has been applied into the computer vision domain, and like in image super resolution, painting, restoring and translation editing, in semantic segmentation also it has been applied, and this anomaly detection and the multimodal generation from text or graph. You can go to the all these data modality, text, audio, and in temporal data modeling, time series imputations, and forecasting, waveform processing, and drug design and life sciences, material design, medical reconstructions, and all there is just future direction. They are just given this third revisiting assumption, theoretical understanding, Latin representations, and diffusion foundation models. So we need diffusion foundation models. So like so this is it for this video. So we will gonna go continue our series on diffusion models from now onward.